This conference will now be recorded.
Hello everyone, this is new chapter which is states of matter, and the topics we are going to discuss. First there will be introduction, and then there is intermolecular force versus intramolecular force. We will compare these two different types of force, and detailed discussion of van der Waals force. Under van der Waals force there is dispersion force, then dipole-dipole force and dipole-induced dipole force. After that, intermolecular force and thermal energy, these two we will compare, and depending on that there is some change in the states of matter. So that is why how to compare these two, that is important. Then physical characteristic of gas, and if time permits we will also discuss Boyle's law. So in introduction for states of matter, so what is matter, that we have already learned in lower class, right? So it will have some mass and it will occupy some space. That is the definition of matter. And if we go to microscopic level, then matter is made up of some tiny particles. And these tiny particles, that is the smallest particles possible, we call it atom. Fine. So anything that has mass and occupies some space, that is actually matter, and it is constituting tiny particles, and these tiny particles are atoms. So this knowledge we already have in lower class, right? Now the properties of this smallest part, that is a single particle of matter, if you consider, it will be molecule in some cases, and if it is monoatomic molecule, then you can call it, that is the smallest part, single particle, you can consider it as atom. So for example, if I am saying any monoatomic gas like helium, then the smallest single particle is single helium atom, because it exists as monoatom. Similarly, if we consider any triatomic or diatomic, for example, you can take O2 or you can take H2O. So in this case, we have some molecule. So the properties that are related to this single particle of matter, it may be helium, it may be H2O or O2, but this is the smallest single particle possible for that particular compound. So these properties that are directly related to this single particle of matter, here you can see some examples. So when we talk about molecular shape, that we have already seen in case of chemical bonding chapter. So it is all about a single molecule, right? We don't consider 4 or 5 molecules together and then we see something. No, it is completely related to a single particle, single molecule. Or when you say atomic size, or in case of molecule, you can also consider an overall size. But that is only for a single molecule or single atom. Or when you consider bond energy, that is the energy between that is required to break the bond that is present between two atoms. So if you take oxygen, there are two bonds present between two oxygen atoms. So to break this, there is some requirement of energy. So that is bond energy, but this is also related to single particle. So this is one kind of properties. And then there is another kind of properties that is not related to single particle. Now it is related to collection of particle of matter. So now in this case, you can consider as if it is from macroscopic point of view, not microscopic, because now you are not considering single particle. Many, that is large collection of particles together you are considering. Then only you can talk about all these properties. For example, boiling property, boiling point or melting point. Then you can consider density or weighting property for any liquid. Because when you consider boiling point means what? You are changing the compound from its liquid state to vapor state. Fine. So when you are talking about this property, obviously that will be related to several molecules or several single particle of matter. Because only when you consider all of them together, then only the question of boiling from liquid to vapor or melting from solid to liquid, all these question arises. Or if you consider density or weighting property, that is a liquid, suppose there are 2 to 3 liquids, but all are all will not have same type of weighting property. Some will be having more weighting properties, some will be having less. But here also, it is not possible with a single particle. You have to consider a large collection of particles. So try to understand the difference between these two types of properties. And we also know there are three states of matter. Mainly we deal with solid, liquid and gas. Though there are some other states also, but that is for our syllabus. That is, even if you do not consider, there is no such problem. So just you can learn about these terms. Except solid, liquid, gas, there are some other states also recently found, which is plasma and Bose-Einstein condensates, that can be seen to exist. But these are, remember, these are special cases, so we will not go into detail of it. So here, solid, liquid and gas, these three states are possible for any matter. So this chapter is states of matter, but why it is important to know that matter is present in which state? Is it present in solid state, liquid state or gaseous state under normal condition? Or there will be some special condition when from normal condition it will be we can convert it to the other state. So suppose that under normal condition we have any metal which is obviously solid, but if you increase the temperature it can be melted. Similarly, water under normal condition it is liquid, but you can change it to solid by decreasing temperature, or you can convert it to vapor by increasing temperature. Okay, but why it is important to know? So basically it is related to physical properties and chemical properties. Okay, now physical properties, when we talk about for any substance, it change with the change of its physical state. So suppose I'm talking about physical properties of water. Okay, now if you are not mentioning properly in what state water is present, by default we can consider it is in liquid form, because that is a normal condition. But suppose if it is not present in water, that is liquid form, suppose it is present in solid form, which is ice, or it is in vapor form, which we call steam. If it is not specifically mentioned, it is not possible for us to talk about the physical properties, because physical properties will be completely different. Though it is same compound, that is chemically it is same, whether water is present in ice form or it is in liquid form or it is in steam form, in all these cases formula is same. Okay, but physical properties are not same. So that is why in which state the compound is present. In this case we have taken water molecule as example. You can consider any other molecule. So in which state the compound is present, that is important for us to know, because it, depending on the state, physical properties may change. Chemical properties of a substance do not change with the change of its physical state. Fine, because chemically it is always H2, 2 hydrogen atom, 1 oxygen atom, there is 2 HO bond. So it has nothing to do with chemical properties. But remember, in which state the compound is present, depending on whether it is solid, liquid or gas, depending on that, rate of chemical reaction will change. Okay, so that is same compound. Suppose you are doing a reaction in solid form, or you are doing another reaction where the same compound is in different form. Suppose it is in liquid form. So chemical reaction, that is rate of the chemical reaction, that will be affected by the states of matter. So these are the reasons that we should learn about the state of matter, how we can change from one state to another, all these things. Fine. Though in this chapter you will mainly find gas, not solid. Solid is there is separate unit for it in class 12, and there is also a little discussion related to liquid, but mainly in this chapter you will find, we will talk about mainly about gaseous, not solid or liquid. So solid not at all, because there is a separate unit for that, and liquid there are some discussions. Fine. So these three states of matter, how we will understand that whether a particular compound, it will be present in solid form or liquid form or gaseous form. So that depends on whether that is what kind of intermolecular forces are present in the molecule, or what about the thermal energy or kinetic energy. So these three states of matter, what is written here, it is the result of balance between intermolecular forces and thermal energy of the atoms or molecules present. So these two are basically opposing to each other. We will go into the details, not here. So when intermolecular forces are very large, there is a tendency that all the atoms and molecules, they will be coming close to each other. And when thermal energy is high, then opposite scenario will be there. Now atoms and molecules, they are going far from each other. So these two are having some that is opposite extreme effect. So when intermolecular forces are high, they are coming close to each other. And in case of thermal energy, it is vice versa, right? So states of matter, it is the result of balance between these two opposing forces. Depending on which one is dominating, depending on that, you will have a particular state of matter. So here, look at this term, it is written intermolecular. Look at the spelling carefully, it is inter, I-N-T-E-R. But there is another term which is intra, I-N-T-R-A. Different spelling. So these two are obviously not same. So here we will mainly discuss intermolecular forces, not intra. But you have to understand what is the difference between these two types of force, because the terms are very, it sounds similar. Fine. So remember, very simple. When I am talking about inter, it is basically two individual molecules. So at least two molecules or two atoms must be there. But when I am talking about intra, it is within same that is molecular atom, within same, and this is between two, whether it is atoms or molecules, whatever, but at least two must be present. Then only you can talk about inter. So intermolecular forces are attractive or repulsive forces. It may be attractive, it may be repulsive. Though in this unit we will mainly focus on attractive forces, not repulsive forces. But repulsive forces may be also. So it arises between interacting atoms or molecules of a substance. So it is atoms or molecules. But intra, it holds atoms together within a molecule. So here it is only about a single molecule. It has nothing to do with another molecule or another atom. Intermolecular forces are much weaker compared to intra. Now it has to be, because here you are talking about two individual entity and you are trying to see whether there is any interaction, repulsive, attractive, this interaction is present or not. But when it is intermolecular forces, here just consider attractive. So for the second point, just consider attractive, because intramolecular forces, mainly we consider chemical bond and ionic bond. Remember, chemical covalent bond and ionic bond. These two types of bonds we have already learned in the previous unit. Okay, so when it is covalent bond that is present between two atoms, or ionic bond present between two atoms, these are actually intramolecular forces. See, if I write any example, just take water molecule. So here this bond H and O, two HO bonds are present. This bond is covalent bond. Okay, so this is actually example of intramolecular forces. So obviously this will be much stronger than the other one, because in other one what you are doing, you are taking two individual molecules. Just take two individual water molecules. So it will obviously be weaker, because here you are actually having some chemical bond. This bond is basically where two electrons, these two atoms, they are sharing with each other. So actual chemical bond is present, so it will be obviously stronger compared to the other one. If we look at this picture, intra, that is inside the molecule or within a same molecule. So this is a chemical bond. Here we have taken covalent bond. It may be, suppose I'm talking about NaCl. We know it is ionic bond, Na plus Cl minus, cation anion and electrostatic interaction. So this interaction, that is also under the example of intra. But when it is inter, now you have to take two individual water molecule, and there is some interaction between H and O. Why we have chosen H and O? If you are thinking why it is not between 2H and 2O, it is because H and O there is some electronegativity difference. So obviously it will be attracted towards each other. It is not that is it will be more important compared to 2H or 2O. But whatever it is, main point is it is between two molecules of water. This is the difference. The first one determine the physical properties of a molecule like boiling point, melting point, density, vaporization, etc. Now it has, you can easily understand it because when we talk about physical properties like this, obviously it is related to a collection of molecules. It is not related to a single molecule. When you talk about single molecule, you can talk about bond energy. Just focus on this line that I have discussed in the first slide. The properties related to single molecule are like this. But when you are talking about a collection of molecules, now you have all these properties, boiling point, melting point, like this. So here also same thing is written. When you want to determine physical properties, boiling point, melting point, this is, which is related to large collection of molecules. Obviously now intermolecular forces you have to consider because that is always between two molecules. So here for simplicity we have taken two, but there will be many other molecules like this. So it will be extended. Okay, but intra it determine the chemical properties of molecules. Now that is also true because if you just take this example of water molecule, you can understand. So when it is inter between two water molecules, depending on this type of attractive force, how strong it is, depending on that, boiling point will be high or low. So if this interaction is very high, then boiling point will be very high. Boiling point means you are converting from liquid state to vapor state. Now when it is liquid state, the distance between two water molecule, and when it is vapor state, now the distance between two water molecule, obviously it is higher in vapor form. So what you are doing, you are basically breaking this interaction by applying temperature, and then only you can increase the distance between two water molecules. So you have to destroy this attractive force. That means here when you we want to know whether boiling point or melting point will be high or low, you have to consider intermolecular forces, because now if you consider intra, that is what is the strength of this bond, it will be of no use, because now we are just trying to separate one water molecule from another, or we are trying to bring them close depending on whether you are melting it or boiling it, whatever. But you have to consider attractive force between two individual water molecules. So that is why this will help us to determine physical properties. But when it is, if you are interested in chemical properties of a molecule, so in chemical properties means the bonds will be now broken. So if water molecule is taking part in any chemical reaction, obviously these bonds between H and O, that will be broken. That means now if you have the knowledge of intermolecular force, it will be of no help, because that is interaction between two water molecules. Now you have to consider intra, because that will give you the necessary information that what is the strength of bond between H and O, because now you are doing some chemical reaction, so you have to break this bond. So that is why the knowledge of strength of chemical bond, whether it is covalent or ionic, that knowledge is in. So these determine the chemical properties of molecules. Okay, so in this way you can compare these two, but now we will switch to only intermolecular force, and we will focus mainly on the attractive intermolecular force. So attractive intermolecular forces, that is collectively, there is a common term we use, which is van der Waals force. Now there are different types of van der Waals force. In this unit mainly we will focus on 3 van der Waals force one by one, and but together that is collective term, you can use this term, which is van der Waals force, in honor of scientist Johannes van der Waals, who explained the deviation of real gases from ideal behavior through these forces. So we will deal with it later. That is ideal gas, real gas, because there also you have heard about this. That is scientist name van der Waals. Van der Waals equation for real gases. All things are there. But right now we will see under van der Waals forces. There are different types of van der Waals forces, but together we use the term for attractive intermolecular forces. Together we use the term van der Waals forces. So it includes dispersion force or London force. So this is number one. Both are actually sometimes dispersion, this word is used, sometimes London. Second is dipole-dipole force, and the third one is dipole-induced dipole forces. One by one we will check all of them. There is another special case of strong type of dipole-dipole, that is under this type 2. There is a specific case which is known as hydrogen bonding. But hydrogen bonding we have already discussed in the previous unit, so that is why it will not be discussed detail here. It is already, we have done it, fine. But it is under dipole-dipole. It is a special case of dipole-dipole interaction, fine. So the first one is dispersion force or London, then dipole-dipole, then dipole-induced. But remember some other terms also you can see in some books, that is other intermolecular forces. So what are the other inter forces? This is ion dipole and ion induced dipole. So in this case, look at the name, some ion is involved. Now when I'm talking about ion, it is fully developed positive charge or fully developed negative charge. But these are not van der Waals forces. So when you are talking about van der Waals forces, there is no involvement of ion, that is no fully developed positive or negative charge. So that is why though these type of intermolecular forces are also there, but that is not under, that is not included under van der Waals force. Fine. So we are not considering this, only these three in the left hand side: dispersion, dipole-dipole, dipole-induced. So in these three names you will not find any presence of ion. Okay. Focus on the first one. Atoms or non-polar molecules. So single atom, for example helium, single atom, because it always exists as monoatomic. You will never find He2, that doesn't exist. Remember in MOT, molecular orbital theory, we have seen it in the last class just, that He2 does not exist. So this is monoatomic, and all noble gases are basically monoatomic. So this type of atoms or non-polar molecules, they are electrically symmetrical. So that is why they are non-polar. Non-polar, polar, all these concepts in chemical bonding we have seen. So how to know whether non-polar or not? There will be no dipole moment. So electrically symmetrical means the charge distribution that is symmetrical. So you will not find that in a particular portion of the molecule there is accumulation of positive charge, or in other part there is accumulation of negative charge. No, it is not the case. It is symmetrical. Even in atoms and such molecules, mean, that is the previous line, what is mentioned, atoms and non-polar molecules. So as it is non-polar, and in case of atoms, no question of polarity possible. Polarity we talk about when there are at least two atoms, that is at least one bond present. Then you can talk about dipole moment or polarity. So that is why when it is simple atoms, no question of polarity. So that is, it is mentioned in the second line that even in atoms or such molecules means non-polar molecules. So though it is non-polar, so we can think that charge distribution is symmetrical, so how any polarity will be generated. But even in atoms and such molecules, temporary dipole may be developed, and that is for a momentary condition. It is not permanent because of some unsymmetrical distortion. So it may happen in some cases. It is actually symmetrical, but suppose for a particular time there is more accumulation of positive charge in a particular portion, and in another portion there will be more negative. So it is a momentary dipole generation, a temporary dipole generation. That is possible. So as if now it is, though it is non-polar, but as if now it is behaving like polar molecule, but it is temporary incident. So see, symmetrical distribution of electrons. So here, suppose it is a particular atom. All these are symmetrical, right? But when it is instantaneous dipole moment due to asymmetry. So now it is instantaneous, that is quick. Now what is happening? All these negative charges, they are on the right hand side, and positive charge it is in the left hand side. So though it is symmetrical, but in the second case, as if now there is some polarity generated temporary. So now what will happen? Suppose this is number 1, and once it is behaving like this, then any neighboring atom, there, now what will happen? Suppose a neighboring atom at a first, this is also symmetrical like this, but when it is in the neighboring position of this first instantaneous dipole, now in the second atom or second molecule, there will be also some polarity generation. So it is true that it is initiated in the first atom or molecule, but now it is also transferred to the second atom or second molecule. So that is why now we are calling it induced, and the induction is coming from the first. So as now there is some negative charge cloud in the right hand side, see what kind of sign I am using? Del sign. So this sign means it is not fully developed negative charge, it is partial development. So because of this negative charge, now this left hand side of this second molecule or atom, there will be some positive charge generation. So this is the first generated instantaneous dipole moment generation because of asymmetry in the charge distribution, and as a result in the second atom or molecule, now there is some induced dipole moment generated in the second atom. So now you can take actual example of helium. So suppose this is the first helium atom, He1, where some, this is a nucleus, but suppose all the electrons, they are in this side. Basically 2 electrons are there, and obviously when electrons are in this side, there will be positive side in the right hand, positive charge in the right hand side. So this is instantaneous uneven distribution of electrons in helium atom. But the second helium, this is symmetrical. You can see it is still non-polar. But how long it will remain non-polar? Not for a long time, because in the left hand side there is already asymmetric electron charge distribution of electron generated already. So it will have now some induction effect on the second helium, and as a result the second helium also will be behaving like this. So this is the first instantaneous dipole, and there is induced dipole on the neighboring helium atom. So similar temporary dipoles can be induced in molecules. So here the examples you are seeing in form of atoms, because that is the easiest way demonstration we can do with atoms, but that is possible. You can also imagine the same thing for a particular non-polar molecule. So non-polar molecule, you can take CCl4 or methane. So this is a non-polar molecule. So similar type of picture you can also consider for non-polar molecules. Now, though we are talking about non-polar molecules and atoms, that is monoatomic atoms, don't think that it will not be present in polar molecules. These forces are basically present in all type of molecules. So see, just apply common sense. If it is possible in non-polar molecules, obviously in polar molecules it will be there. Okay, because non-polar, if it can exist, so in polar molecule there is already asymmetric electron charge distribution. So obviously now the process will be further assisted. So don't think it is exclusive for non-polar, it is also possible for polar molecules also. Larger and heavier atoms and molecules exhibit stronger dispersion forces than the smaller and lighter ones. Now when mass will be very high or heavier atoms, So just if you talk about atoms, suppose I am considering helium. So in noble gaseous, this is very small, that is the smallest one. But if you take suppose xenon, which is heavier obviously compared to helium, so in this case, this dispersion force will be very high. So it is directly related to the mass. So when mass is high, suppose you have taken two similar type of molecules, and you are trying to compare in which case it will be having more dispersion or London force. Obviously, the heavier one or where the mass is high, that will have more dispersion forces. Because what happens when it is very large and very heavy, now the electron charge cloud, that is the number of electrons are very high. So this distortion in the electron cloud or this redistribution of the electron cloud, that process will be now facile. So that is why larger and heavier atoms, they will exhibit stronger dispersion forces. Then easily polarizable atoms and molecules, they will also have stronger forces than less easily polarizable ones. So polarizability or polarizing power, all these terms we have already learned in Fezan's rule. Remember in Fezan's rule, in chemical bonding chapter, we have already seen this. So we know how to understand in which case polarizability will be high. So when it is easily polarizable atoms, that is where the redistribution of electric charge, it will happen very easily. That is actually polarizable. It is not very tight electron cloud, it is loose type. Okay, so polarizable atoms and molecules, they will have stronger forces than less easily polarizable ones. So these are some points on which dispersion force will be high or low, that is dependent. It is criteria how to understand in which case dispersion force will be high. Fine, that is related to mass and how far how easily polarization is possible. Depending on that, dispersion force will be high or low. Now it is obviously related to distance, as this is a very that is weak type of force. So when these two atoms, just take this example, we have two helium atoms. So when these two helium atoms are very close to each other, then only it is possible. And from this term, you can easily understand how this distance is affecting. So it is inversely proportional to 1 by R6, where R is the distance between two particles. Basically, it is inversely proportional to distance. Don't think it is directly inversely proportional to 1 by R6, because if I say so, then it means as if it is directly proportional to R6, because it is already given 1 by R6. So basically it means when R is very, very small, then only it will be very high. So it is inverse. Distance small, dispersion force high. And it is being present in denominator. So that is why and R to the power 6. That means suppose R is very low and as there is power 6. So this denominator, it will be very, very high. And it is in denominator, that means a little change in distance. Suppose in some cases I have taken R is 2 ppm, another case I have taken 3 ppm. So 2 to the power 6, and you have just changed the value from 2 to 3. Now it is 3 to the power 6. So the effect is very high, and that is present in denominator. That means overall effect, dispersion force, that is very high. So it is inversely proportional to distance. These forces are important only at short distance. So that is what is already mentioned here, because it is happening mostly in non-polar molecules. And if you are, they are already non-polar, that is symmetric charge distribution. And if somehow in one atom instantaneous dipole is generated, and it will, to show the effect on the next neighboring atom, the distance must be close. If the second helium is very far, then this effect is not possible. So short distance is important. And remember, compared to other type of intermolecular forces, this is the weakest type, because there is that is instantaneous generation, then only some induction is occurring, and then there is interaction is happening between two positive charge, del plus del negative. Okay, so this is very weak. Here we have some examples where you can see basically London forces or dispersion force you can see in any molecule, but mainly we give it importance or consider it significant for non-polar molecules mainly. So here you can see halogens. In general, I have written halogens. You can consider bromine, fluorine, chlorine, iodine, all are diatomic. Then noble gases. So basically in noble gases, you will not find any other type of intermolecular forces, though we have not learned yet other type of forces, but when you will learn it, you will see that other forces that we are going to discuss next. Dipole-dipole, dipole-induced dipole. These are not possible in noble gases because noble gases they are monoatomic. There is no question of polarity. So for noble gases, this dispersion force is very important because that is the only force possible here. Fine. So xenon, neon, krypton, all these you can consider noble gases, and then we have carbon dioxide. So carbon dioxide, this is non-polar molecule because both sides you have C double bond O, and that is the reason one uh, dipole moment it is cancelling the other one. The direction is in the opposite side. So overall dipole moment is 0. Then we have another example, phosphine. Now phosphine is not a non-polar because it is like this. There is a lone pair. So it is not symmetrical molecule, and I cannot say that it is no non-polar, but still you can consider because this type of forces is also applicable for polar molecules. Then we have any type of hydrocarbons. In organic compounds, if you consider different types of hydrocarbons, suppose ethylene, ethane, where carbon and hydrogen, these two are present. So they are mainly non-polar because dipole moment, because of very low electronegativity difference, dipole moment is, sorry, there is a spelling. Dipole moment is not so significant in these type of molecules. So for hydrocarbons, where carbon and hydrogen, these two atoms are present, that is hexane, benzene, etc., CH4. Here also you can consider as example. Then carbon tetrachloride, CCl4. It is just like methane. Only difference you have 4 chlorine instead of 4 hydrogen. Fine. So these are the examples. After dispersion force, next is dipole-dipole force. So as the name says, dipole-dipole. So you have to consider some dipole. Dipole means this type of thing, where in the molecule already there is some charge separation. So already there is asymmetry in electrical charge distribution. So this is suppose number 1 dipole, this is a second dipole, and there is del negative, del plus. So there will be some interaction between these two. Fine. So it will remain in this way. It is not that the negative will be close to negative because there will be repulsion. So the molecules, they will be arranging themselves in this way. So when this force possible, it will occur between molecules where already dipoles are present, permanent dipoles, not instantaneous dipoles that you have seen in the previous case. But now it is permanent dipoles. So polar molecule you have to consider because without polar molecule, how you will get permanent dipoles, right? So see here we have taken this interhalogen ICl. So it is just like diatomic iodine or diatomic chlorine, but now the bond is not between two same atom, it is between I and Cl. So obviously there will be some difference in electronegativity. Chlorine is more negative, so negative side will be towards chlorine, positive will be towards iodine. Now another ICl molecule, it will arrange just below the first one. It will be, its orientation will be like this, so that the negative is close to positive positive dipole, and the negative is towards iodine. But if it is in the linear form like this, then ICl, then it will not be like this. That you cannot write. Okay. So after Cl, another molecule is when you are writing, you have to write I first. So this type of interaction possible. Then you can consider water molecule, because water molecule, why we have chosen this, because there is already polar bond present. We know there is the electronegativity difference between H and O. So this side will be negative and this side will be positive. So this is the first water molecule, second water molecule, third water molecule, and the fourth one. So see here the negative del sign over oxygen. So there will be interaction with the hydrogen of the second water molecule. Then the second water molecule's oxygen interaction with the third water molecule's hydrogen, and so on. So all these interactions are dipole-dipole forces. For molecules of similar size and mass, the strength of these forces increases with increasing polarity. So see, here we have fixed this point. That means if you have taken two, suppose you just want to compare in which case dipole-dipole forces high, but they are varying in size and mass. There is high difference. So in that case you cannot compare, because size, mass, that is also important, directly related to intermolecular forces. So when mass is very high, the force will also be very high. So if you have not keep this point fixed, you cannot compare how the dipole-dipole force will change with polarity. Suppose you have taken molecule 1, you have taken molecule 2. So first you have to check whether their masses are close to each other or not. When they are close to each other, then only, or their size is close to each other, or sometimes shape also matters. So when these are almost same, then only you can consider this how it is related to polarity. So as it is dipole-dipole force and present in permanent dipoles, obviously if polarity is high in the first molecule, you can easily say that dipole-dipole force will be high in the first molecule. But remember, provided similar size and mass, because if 1 and 2 are not similar size and mass, that point will also have some effect, and in that case you cannot compare that with increasing polarity whether dipole-dipole force will be less or high. Okay, this interaction is stronger than the London forces, that is the previous one, but it is weaker than ion-ion interaction. Though it is true that ion-ion interaction is not under Van der Waals forces, but we are just comparing here that its effect is in between. So it is very easy to understand, and you can easily relate it, because London forces, it is very weakest, that we have already seen. And when you have any molecule where permanent dipole is present, so obviously it will be having more intermolecular force between them, more attraction will be there, because already there is some dipole. It is not that it is generated instantaneously, it is already present. So compared to London forces, it will be stronger. But if you consider ion-ion interaction, where you have one ion, suppose the molecule is ionic, X plus X minus, then another molecule X plus Y minus, so there will be some interaction between Y minus and X. This is one molecule, this is another. So here already some ions are present, so obviously it will be having more interaction. But when we are talking about dipole, it is not free negative charge or free positive charge, it is not fully developed charges. So that is why compared to ion-ion interaction, it is weaker, but it is stronger than London forces. Here also it is dependent on distance. So dipole-dipole interaction is interaction energy between stationary polar molecules. That means when it is in solid form, any compound, then it is proportional to 1 by R3, or you can say it is inversely proportional to R3. But when it is in not polar, the solid form, suppose you have taken any rotating polar molecule, in that case now it is proportional to 1 by R6. Fine. Besides dipole-dipole interactions, if you have any polar molecule, don't think that there will not be any London forces. And this point already I have mentioned in the previous course also, that it is not necessary that London force will also only be present in non-polar, it can also be present in polar. But mainly we give significance to London forces for non-polar molecules. But in polar molecules, that is beside dipole-dipole, they can also interact by London forces, though this is more important when the molecule you have taken already having some dipole moment. Obviously, you have to give more priority to dipole-dipole, but that doesn't mean London forces are not present. It is also present. The third one is dipole-induced dipole. Try to understand difference. In the previous case, it is dipole-dipole. That means you are considering interaction between two dipoles or two molecules having permanent dipole moment. But now, one species is dipole having permanent dipole moment. Another one is not permanent dipole, but it is induced. Okay, so it will be generated. So dipole-induced dipole forces are weak attraction that results when a polar molecule induces a dipole in an atom or in a non-polar molecule. So in one side you will have a polar molecule, I am writing polar. Another species will be non-polar. So this polar, it is already having some, that is electron distribution, it's not same. So suppose one side it is negative, another side it is positive. So now what will happen, because of this type of dipole nature, it will induce the non-polar molecule, because if you consider simply the non-polar molecule, there is symmetrical charge distribution. But when it is close to this polar molecule, now there will be some induction, and it will disturb the arrangement of electron on the non-polar molecule. And as a result, now there will also be generation of del minus and del plus. So here you can take any oxygen molecule. So when it is isolated, obviously it is non-polar because you have same atom both sides. But suppose now you have taken a water molecule. So water molecule is having permanent dipole, but oxygen is not having any polar nature. But when this water molecule is present close to this oxygen, now there will be some disturbance in the electron charge cloud, and as we have written the water molecule, see, oxygen is in the towards, that is oxygen atom is towards O2 molecule. That means oxygen side is del negative, this side is del negative. So that is why after this induction, right hand side of this diatomic oxygen, there will be del plus sign. But suppose if you are writing the water molecule in this way, then it will be opposite. Now in this non-polar molecule, del negative will be this side, del positive this, because now I have written H atoms towards O2 molecule. Okay, so depending on how you are drawing, depending on that, the induced dipole you can write draw, that is which side you will place del negative or del plus. But important point is, one species will be polar, that is having permanent dipole like water molecule, but another species at a, that is isolated condition, is non-polar, but in presence of this polar molecule, now there will be some induction. Here also interaction energy is proportional to 1 by R6, where R is the distance between two molecules. Fine. Induced dipole moment depends upon the dipole moment present in the permanent dipole. That means here if you consider water molecule, how much induction will be there, that depends on the polarity of the molecule that you have taken. So here we have taken water molecule as polar molecule. So suppose instead of water, if you have taken any other molecule which is having low polarity compared to water, now it will have less induction effect on O2 molecule. So that is mentioned here. The induced dipole moment depends upon the dipole moment present in the permanent dipole species. So this is the permanent dipole species, this is the non-polar species. So depending on how much dipole moment is present, so if I am writing P1 and this is P2 and NP is common, and P1 if it is having higher dipole moment compared to P2, so obviously P1 will have higher capacity to induce the, that is to induce the charge separation in the non-polar species. So that is mentioned here. Beside dipole-induced dipole interaction, London forces are also present. So this line you have already also seen in case of dipole-dipole. So London forces will always be there, but when you have these two different types of species, you have to give importance to this dipole-induced dipole type of interaction. Here we have a question. It is saying that dipole-induced dipole interaction, that is the last force that we have discussed, present in which of the following pairs? So first of all, you have to remember one molecule polar, another molecule must be non-polar. This combination you have to keep in mind. The first option we have HCl, which is obviously polar. Helium is non-polar. So this can be our answer. But we'll also check the other ones. SiF4. Now it is just like methane. You have that is tetrahedral type of structure, and all these SiF bonds, they are cancelling each other. So overall the molecule is not polar. So it is non-polar. So it is non-polar combination. So this cannot be correct. Then you have H2O molecule and alcohol. But H2O molecule and alcohol, both are alcohol, you can write in general ROH. Now this is polar, this is also polar. So this is polar combination. So this is also not possible. And the last one, chlorine and CCl4. Now this is NP-NP combination. So correct option should be first option. Second question, ammonia's unusually high melting point is the result of which one? Here we have dipole-dipole forces, London dispersion forces. These two we have learned in today's class. Hydrogen bonding, I have mentioned, it is a special case of dipole-dipole. Remember, it is already mentioned in the slide where van der Waals I have started. So this is a special case of dipole-dipole. So in hydrogen bonding, when it is possible, when you have, obviously hydrogen should be present, and there should be bond with any heteroatom, and this heteroatom either F, O or N, any of these three, when present, then only hydrogen bonding possible. And hydrogen should be directly connected to this heteroatom. So you can observe it in water molecule, in HF molecule, and here also we have ammonia molecule, that is NH3, where you have 3 NH bonds, and all these bonds, they are capable for hydrogen bonding. And we are talking about melting point, why it is high. Obviously that will not depend on covalent bonding, because this is not inter, this is intra. So how it can be possible? You have to choose anything between ABC, not D. But ABC, it is true that ammonia is polar, so dipole-dipole will be present, and London dispersion, that is always present. But which one you will choose? This is a single correct choice. You have to give priority to hydrogen bond, because here hydrogen bond is possible, and when suppose 3 or 4 forces are possible, and you have to choose which one is more significant, obviously you have to give significance to that force which is dominating over others. Now London force, it is not so dominating like dipole-dipole, and hydrogen bonding, this is stronger compared to dipole, though it is a special case of dipole-dipole. But remember, when it is H and any electronegative atom FON, so the electronegativity difference between these two is very high. So the polarity that will be generated, that is also very high. So that is the reason hydrogen bonding, it is obviously stronger compared to dipole. So as this is most, that is stronger compared to the other two, so that will be the correct option. So hydrogen bonding is possible between two ammonia molecule, and because of this hydrogen bonding, it is difficult to separate ammonia from each other, because here we are talking about melting point, that is you are converting from solid to liquid. Okay, so you have to give priority to hydrogen bond. Fine. Which substance has the highest boiling point here? So here we have CH4, which is non-polar. Then we have helium, which is monoatomic. This is also non-polar. Now HF, obviously this is polar, and here hydrogen bonding is also possible. Basically here dispersion is possible, dipole-dipole possible, but hydrogen bonding you have to give priority. So that is why it will be the right, and chlorine is also non-polar. Which has the highest boiling point? Now all are basically noble gases, and we know when it is similar type of species, you have to consider in which case mass is high. So here maximum mass is for xenon, then krypton, then argon, then neon. So that is why xenon should be the correct answer. Fine. Higher mass, higher more intermolecular interaction, and boiling point is accordingly very high. So we will end here. Though I have mentioned the topic thermal energy, but because of a lack of time, we are ending here. Thank you for listening.